Good morning, dear students, and once again, welcome back to our course. In the last lecture, we discussed in detail about the fundamental aspect of parameters which plays an important role in order to analyze the behavior of a circuit. And I told you that the difference between a network and a circuit. So, as far as network is concerned, it is nothing but a kind of a structure where we have a combination of open loop and closed loop. Whereas if we are dealing with a circuit, it is nothing but a kind of a structure where we have only closed loop. So whenever we are dealing with a kind of structure where in that structure, if we have 5 elements and all the 5 elements carry a finite value of current, then we can treat that particular structure as a circuit. So I can say that all the circuits are network, but all networks need not to be a circuit, because a network has to be a circuit if and only if it consists only closed loop. But the moment we have a combination of open loop followed by closed loop, then that structure is known as network. This is very important. Then we discussed in detail about the concept of electric charge followed by electric current, then electric potential, then potential difference. Then we also discussed in detail about the fundamental aspect of power, energy, then different formulas to calculate power, energy, and then we solve some numerical on that. So finally we conclude that electric charge is indicated by symbol Q, and the unit for electric charge is coulomb, and it is defined as a fundamental property of a particle through which it is going to experience a force when they are placed in the presence of electric field. In the same way, we define the concept of current indicated by symbol I, and the unit for current is ampere. And what is electric current? It is simply rate of flow of charge. So I can write I as Q by T. Then we discussed in detail about the fundamental aspect of electric potential indicated by symbol V, and it is defined as energy per unit charge. So energy per unit charge is nothing but electric potential, and the unit for electric potential is joule per coulomb or simply volts. This is very important. And then we also discussed in detail about what sign conventions which we need to follow in order to do the analysis for circuit theory. For example, if we are moving from positive polarity to negative polarity, that means we are experiencing a voltage drop. And when we are moving from negative polarity to positive polarity, that means we are experiencing a voltage rise. Then we also discussed the concept of potential difference. It is simply the difference between the potentials at two different points. For example, if we have 2 points, one is at A and another one is at B. Suppose the voltage at point A is VA and the voltage at point B is VB. So the difference between voltage or potential is simply VAB, which is nothing but VA minus of VB. And the unit for potential difference is again going to be volts, or you can say joule per coulomb. Then we discuss the concept of power. So power is simply energy per unit time, or we can also define this as V into I, or we can write the same expression as I square into R, or we can write this equation as V square divided by R. In the same way, we define the concept for energy. Energy is nothing but power times current. We can define this as Vi into T, or we can write this equation as I square into R into T, or we can write this as V square by R into T. All are nothing but same. The unit for power is watt, and the unit for energy is joule, or we can also define this as watt second, or sometimes this we can also define as watt hour. The thing is that it depends upon the unit in which we express time. Suppose we express time in second, then it is going to be watt second. Suppose we express time in hour, then the unit for energy is going to be watt hour. And normally in electrical domain, this unit we need to prefer in order to indicate the amount of energy. So all these points we have discussed in the last lecture. Now let us try to start our today's session, where we are going to discuss the fundamental aspect related to different types of elements which are normally available in electrical as well as electronics circuit. So what are those kind of element and how to classify circuit element? Also we are going to discuss in detail about the fundamental aspect of what is source and how to classify source, the meaning of ideal voltage source, then ideal current source, practical voltage source, practical current source, and finally we're also going to look in detail about the aspect of dependent and independent sources, and by the end of this session we are going to solve some numerical on those topics. So let us begin with our today's session, and let me tell you one thing, that this topic is again common for both, because in the very first lecture of this course I inform you that whatever the topic which I am going to take in this particular sessions are normally common for both electrical as well as electronics and communication engineering students. So the first topic which I am going to cover in this lecture is simply the classification classification of circuit element. Now suppose if you want to design a circuit, then what kind of elements are normally available with us through which we can define or we can construct a circuit? So how to classify circuit element? So basically the circuit elements are classified into two main domain. First one is called as active element, active element, and second one is called as passive element, passive element. Now active elements are nothing but those type of elements which are available in a circuit, which basically going to act as a source for energy. So sometimes these elements are also called as a source for energy, because they are going to supply the energy or supply the power. Whereas passive elements are nothing but a kind of elements which are available in the circuits, which will not supply energy, but at the same time they are going to either dissipate energy or they are going to store the energy. But remember one thing, that these type of elements are not supposed to supply energy initially. That means a kind of element, if they are designed to dissipate energy in the form of heat, or if they are capable to store energy either in the form of electric field or in the form of magnetic field, those type of elements are called as passive element. That means they are not going to supply energy by their own. Whereas active elements are treated as a source to supply energy depending upon the requirement of the circuit and depending upon the requirement of the load. Now these passive elements, depending upon whether they are designed for energy dissipation or they are designed for storage mechanism, we can classify them into two main category: a kind of passive elements which are designed for energy dissipations, and then a kind of passive elements which are designed for energy store. So in this category, that means a kind of passive elements which are designed for energy dissipations are simply resistors, indicated by symbol capital R. So here we have resistors. So what is resistors? Resistors are nothing but a kind of passive elements which are designed for energy dissipation. And normally resistors dissipate energy in the form of heat. That means if you have a resistor indicated by this particular symbol, Let capital R indicate the resistance of this particular resistor, and to this resistor if we pass a finite value of current, then according to Joule's effect, which is nothing but I square R into T, this resistor is basically dissipate electrical energy into heat energy. So this is very important. In the same way, in this particular category, that means in storing mechanism, depending upon the way a passive element is going to store energy either in the form of electric field or in the form of magnetic field. Based on that, we have two more fundamental passive elements under this particular category. First one is called as inductor, and second one is called as capacitor. So inductors are normally indicated by symbol L, and capacitors are normally indicated by symbol C. So inductance property is basically L, and capacitance property is basically C. And inductor stored energy in the form of magnetic field, whereas capacitor stored energy in the form of electric field or electric charge. This is very important. So ultimately, passive elements are nothing but a kind of elements which are available in the circuit, which are designed for either energy dissipation or for energy storage mechanism. If a kind of element which is designed for energy dissipation in the form of heat, so those kind of elements are nothing but resistors indicated by symbol capital R. In the same way, if the elements are designed for storage mechanism either in the form of magnetic field or in the form of electric field or electric charge, then we can treat them as inductor and capacitors respectively. So in the category of passive elements, the most fundamental element which are commonly used for the designing of any network or any electric circuits are nothing but R, L, C, where R is resistor, L and C are inductor and capacitors respectively. Resistors are designed for energy dissipation, whereas inductor and capacitors are designed for storage mechanism. But ultimately, all these three are nothing but passive element because they are not going to supply energy by their own. Either they are going to dissipate energy or they are going to first store that energy, and then depending upon the requirement they will release that particular energy in the circuit. That is very important. Now let us come on this side. So here we have active element. What is active element? A kind of element available in a network or a circuit which are basically designed for supplying energy. So basically they are going to act as an excitation. So how to classify this? So active sources are further classified into two main domain. First one is called as ideal active element, ideal, and second one is called as practical, practical active element. Now under the category of ideal, again we have two more bifurcations. First one is called as ideal voltage source, voltage source, and here we have ideal current source. In the same way, under the domain of practical, again we have two more bifurcations. First one is called as practical voltage source, and second one is called as practical current source. So what is the meaning of this? Why we have two different kinds of domain for active element? First one is called as ideal and second one is called as practical. And again in ideal we have two different kinds of sources. It may be ideal voltage source or it may be ideal current source. In the same way, under the category of practical, we have practical voltage source, or it may possible that we have practical current source. So let us try to discuss all these kind of element in detail one by one. So what is the meaning of this ideal and what is the meaning of this practical sources? Now see here, First, we will discuss what is ideal voltage source. So, what is voltage source and why this particular source are treated as ideal? Now, see here, voltage source is nothing but a kind of active element that are responsible to create a potential difference in the circuit. So, if we have a source or an active element, and if that particular element promises that it is capable to maintain a constant potential difference across any 2 point in a network or in a circuit, then that particular element we are going to treat as a voltage source. And ideal voltage source are normally indicated by symbol like this, a circle with fixed polarity plus minus. So this is for ideal voltage source, that too for DC. Suppose if you want to indicate this for AC, then in that case we need to draw the structure like this or symbol like this, a circle with sine wave inside this. And just to make sure that to have an ease in order to apply network theorem, we need to indicate its polarity. But remember one thing, because it is a sinusoidal, this polarity is going to change depending upon its frequency. But just to have a ease in order to apply network theorem, we have to indicate initially that what will be the polarity of a AC circuit. But this is going to be changed depending upon the frequency. So this symbol is for DC and this symbol is for AC. But the beauty is this is ideal voltage source. Now why is called as ideal voltage source? Let us consider that the magnitude for this particular voltage source is say a volt, where A indicate the magnitude and this V indicate the unit for this particular quantity. Or I can rewrite this as any finite value. For example, say 100 volt. So here 100 is nothing but A, where A indicate the magnitude of this particular voltage source and this V indicate the unit for this particular voltage source. Now why it is called as ideal? Ideal voltage source means what? A type of voltage source which is capable to supply constant value of voltage irrespective of the load connected across it. For example, if you connect, let us consider over here a circuit, and suppose the voltage value of this voltage source is say 100, and if this particular voltage source is of ideal category, then this voltage source is capable to supply a constant value of 100 volt as an output irrespective of a load connected across it. यहाँ लोड आप कितना भी लगाओ और लोड को आप कितना भी वैरी करो, irrespective of the load connected across this particular voltage source, it is capable to supply 100 volt continuously. And then this particular voltage source is called as ideal voltage source. So suppose if you want to draw a graph of this voltage delivered by this voltage source with respect to a load connected across its terminal. So irrespective of the load, where it is 0 or 10 or 100 or 1000 or infinite, the magnitude of voltage supplied by this voltage source, which is in our case is say 100 volt, is almost going to be a constant one. It is not going to change. So if we have a kind of voltage source which is promises us to exhibit this type of property, that means irrespective of the load connected across it, it is capable to supply a constant magnitude of voltage, then that type of voltage source are called as ideal voltage source. But practically this is not the case. Now what is practical voltage source? Practical voltage source is nothing but a type of voltage source in which the magnitude of this voltage is going to reduce as we increase the value of load. So the graph for practical voltage source is something like this. It is initially when we have not connected any load, the magnitude is exactly going to be equal to 100, And the moment we increase the value of load, the terminal voltage is going to be reduced like this. This is very important. So this is the variation of voltage with respect to load for practical voltage source, and this is for ideal voltage source. So this is very important. Now the thing is that why this voltage is going to reduce, and the answer for this is internal resistance. Internal resistance of the source, because of which the value is going to reduce as we increase the value of load. That is important. Let us consider that the internal resistance is indicated by symbol small r in. So the thing is very clear that in case of practical voltage source, the value of output voltage is going to reduce because of this internal resistance. So in this particular symbol, so this indicates the symbol for ideal voltage source. So suppose if you are interested to draw the symbol for practical voltage source, so what will be the symbol for practical voltage source? So it will be something like this. See, here we have a ideal voltage source, so this is going to be plus, this is going to be minus. Let us consider that the voltage delivered by this ideal voltage source is say V volt, or you can treat that any value. And then somewhere over here we need to indicate the resistor, which is nothing but the internal resistor of this particular source. Now it may possible that we may connect them in parallel, we may connect that particular resistor in series. Now suppose if we connect the internal resistance of that voltage source in parallel with this particular symbol, which is nothing but R in, then what will happen? Now see here, because this indicate your ideal voltage source and the internal resistance of the source we have connected in parallel, and we know that in parallel combination voltage will remain same. That means if we have V volt generated by an ideal voltage source, the same V volt is going to appear over here, which is nothing but V. But practically, as the value of load increases, the magnitude of voltage supplied by ideal voltage source is going to reduce. So this phenomena is not possible over here, because if you connect a load over here and if you increase the value of load, because we have connected ideal voltage source and the internal resistance in parallel combination, the same value of voltage is going to appear over here irrespective of the load. But practically this is not the case. The moment we increase the value of load, the terminal voltage has to be reduced. So to exhibit that particular phenomena, what we need to do, we have to connect a ideal voltage source like this and the internal resistance of the same source in series combination. This is very important. So here we need to connect R in. Now this symbol is for practical voltage source, which is very important. Now suppose if you connect a load over here, suppose if you connect a load over here, now if you vary the value of load, the moment we connect a load, there will be a flow of current through this particular circuit, and there will be a dissipation of energy across this particular internal resistance, and the drop which we are going to experience is nothing but I into R in. So this I into R in indicate the drop across the internal resistance of this particular source. Now depending upon the value of load we have connected over here, the value of I is going to vary. Because R in is constant, hence this particular term is going to vary depending upon the value of I, which in turns is going to vary depending upon the value of load. Now initially, suppose the load is 0, the value of I is going to be 0. So we can easily identify that the value of V which is available across this particular load, suppose that V is nothing but say Vt. So I can write here as Vt is nothing but V minus I into R in. So initially as load is 0, I is going to be 0. So this particular term is going to be 0. So we can treat that as Vt equals to V. That means this particular condition. And the moment we increase the value of load, that means we increase the value of current, this this particular term is going to increase. And the moment this term is going to increase, because V is constant, so V minus increasing value, this particular term is going to be reduced. So the moment we increase the value of load, we are reducing the value of voltage like this. So this is what the practical significance of a voltage source. So ultimately we conclude that if you have a voltage source, that to a practical one, so it must be indicated by this symbol. A ideal voltage source having a value say V, then we need to indicate its internal resistance indicated by symbol R in, and here we have a terminal voltage which is nothing but Vt. This is very important. So this symbol is for practical voltage source. I hope this point is clear to everyone. Now let us try to discuss the concept of ideal current source and practical current source. So again, what is ideal current source or practical current source? So first discussed ideal current source. So ideal current source are indicated by symbol like this, a circle with arrow. This arrow indicate that it is nothing but a ideal current source. Let us consider that the magnitude of this current source is I and the unit is A. So I indicate the magnitude and A indicate its unit, which is nothing but ampere. Now what is ideal current source? It is a type of active element which is capable to supply constant value of current irrespective of the load connected across it. That means if you draw a graph between current and the load, so somewhere over here we need to take a current. Suppose on x-axis I have taken a current, and suppose on y-axis if I take a load, so this indicate a constant value. That means irrespective of the load connected across it, the value of current is almost going to be a constant one. And the moment we increase the value of load corresponding to that, the value of current goes on decreasing. So this is due to the internal resistance of this particular element. Now suppose if you want to draw the symbol for a practical current source, so how it is going to be? So again, in this particular case, we need to indicate or we need to add its internal resistance. Then we may have two conditions for this. We may connect that in series or we may connect that in parallel. Now suppose if we connect the internal resistance of a current source in series with ideal, now how it is going to behave like this? So see here, the moment we connect the internal resistance of a current source in series combination with ideal one, because we know that two elements when they are connected in series combination, the value of current will remain the same irrespective of load connected across it. But this is not the practical condition. The moment we increase the value of load, the value of current goes on decreasing. That means the internal resistance of a current source need not to be connected in series. It has to be connected in parallel combination. So this is not the representation for your practical current source. So practical current source, or I may write this as practical current source, it is something like this. So first we have a ideal current source indicated by symbol I, ampere, and then to this we indicate its internal resistance which has to be connected in parallel. This is very important. So here we have R in. You may indicate by capital R in, or you may indicate this by small r in. Both are nothing but same. But remember one thing, as far as practical current source are concerned, the internal resistance has to be connected in parallel with the ideal current source. Now, why we need to connect this in parallel? Just to fulfill this particular condition. The moment we increase the value of load, the value of current has to be reduced. This is very important. Now, see here. Let us consider that the current delivered by this ideal current source is, say, I ampere. So this I ampere is coming up to this particular point. Now, what will happen? Some value of current is flowing through this particular resistor, which is nothing but R in, and the remaining value is flowing through this circuit if you connect a load over here. Let us consider that the value of current flowing through the load is, say, IL, and let us consider that the value of current flowing through the internal resistance is, say, R I in. So if you apply law of conservation of charge at this particular point, we can write the current entering a node, which is nothing but I, is going to be equal to the current which is flowing out from that particular junction, which is nothing but I in plus IL. Now, practically, we want this I and this IL must be the same. That means if this ideal current is capable to deliver 10 ampere of current as an output, then the entire 10 ampere must be available over here, which is nothing but load current. This is possible only when the value of this internal current, or you can say the current flowing through internal resistance, is nothing but 0. Now, this is possible only when the value of this internal resistance is going to be infinite, because according to Ohm's law, we know that I is inversely proportional to resistor. That means if you want to reduce the value of current, we have to increase the value of what? Resistor or resistance. So the same logic is implemented over here. Just to make the value of I exactly equals to IL, the value of I in must be 0. And ideally, to make the value of I in as 0, we need to put the value of R in as infinite. Or this is possible when we put R in as infinite. This is very important, because from this particular expression we conclude that the internal internal resistance of an ideal current source is going to be infinite, and the internal resistance for a practical current source is as high as possible. This is very, very important. So this you have to remember. The same logic we can implement in case of a voltage source. For example, if you have a voltage source, maybe say ideal or a practical, and suppose if you are interested to find out what will be the value for resistor in case of ideal voltage source or in case of a practical voltage source. So see here, this is the symbol for ideal voltage source, say V, and then in series with this we need to indicate its internal resistance, say R in. And suppose we are interested to find out what will be the value of terminal voltage available across a load, which is nothing but, say, Vt. So mathematically, if you apply law of conservation of charge, because we know that volt is nothing but energy per unit charge, so if you apply law of conservation of energy over here, we can write this as V minus I into R in is going to be equal to Vt. Or simply you can write this as V is equals to I into R in plus Vt, where I is the value of current flowing through this particular circuit in this particular direction. So if you want to make this V and Vt as same, we want to make this particular factor as 0. The moment we design a voltage source which is capable to offer 0 internal resistance, then in that case the value of this I into R in is going to be 0. And the moment the value of I into R in is 0, the value of V is exactly going to be equal to Vt. And this is what our ideal condition is. For example, if this voltage source is capable to deliver 100 volt as an output, so ideally we want this entire 100 volt has to be appear across a connected load. This is very important, and this is possible only when the internal resistance of a voltage source is nothing but 0. So finally we conclude that the value of internal resistance in case of ideal voltage source is nothing but 0, and in case of practical voltage source as low as possible. So I can indicate our final conclusions like this: indicate a ideal voltage source, and this indicate plus minus with internal resistance in series as a practical voltage source. So this is Rn and this is nothing but V. So this is practical voltage source, and the value for internal resistance in case of practical voltage source is 0 or as low as possible. Ideally it must be 0 or practically as low as possible. Whereas in case of ideal current source, so this symbol is for ideal current source, and suppose if you are interested to indicate the practical one, so it is something like this. So here we have an ideal current source, and in parallel with this we need to indicate a resistor which indicate the internal resistor of this particular element. So this is for practical current source, and in case of practical current source the value of internal resistance must be infinite or as high as possible. So this is very important. So finally we conclude that the internal resistance in case of ideal voltage source is going to be 0, in case of practical as low as possible. The internal resistance in case of ideal current source is going to be infinite, and in case of practical as high as possible. So this you have to remember. Now once we done with this, let us try to discuss another domain to classify active element. As I told you that active elements are classified into two main category: practical, ideal. And in practical we have practical voltage source, practical current source. In the same way, in ideal domain we have ideal current source as well as ideal voltage source. So active elements are further classified depending upon whether their values are dependent on the performance of other circuit elements or not. So based on that, we can further classify these active elements into two main category. First one is called as dependent sources, and second one is called as independent independent sources. Now what are independent active element? Independent active elements are nothing but a kind of active element, or you can say a kind of sources whose values are almost going to be constant. They are not going to depend on the performance of some other circuit element available in that particular structure. For example, just we discussed like ideal voltage source, or you can say practical voltage source. In the same way, ideal current source followed by practical current source. So these are the example for independent active element. That means once we have decided that the value of that practical voltage source is say 100 volt, then it is going to be 100 volt. The value is not going to change due to the change in the performance of some other element connected in the same circuit. That means their values are independent on the performance analysis of some other circuit element. That's why they are called as independent. Whereas dependent element are a kind of active element where their values are dependent on the performance of some other circuit element available in the structure. Now, based on this, whether their values are dependent on a voltage or a current, we can again bifurcate this dependent active element into two main category. First one is called as voltage controlled. Second one is called as current controlled. For example, if you have active element like voltage, then the value of this voltage source, it may possible that depends upon the voltage across some element available in that particular circuit. In the same way, it may possible that the value of this voltage source may also depends upon the value of current flowing through some element in the same particular circuit. So depending upon that, this dependent active elements are further classified into two main category. First one is called as voltage control, second one is called as current control. And in voltage control, we have again two main type. It may possible that it is nothing but a voltage source which is controlled by a voltage. So this we can treat as a voltage controlled voltage source. It may possible that we have a current source, but that current source value is controlled by voltage. So I can treat this as voltage controlled current source. So this Vs indicate that it is a voltage source, but the value of that voltage source is controlled by some voltage across some element available in that particular circuit. That's why it is called as voltage controlled voltage source. And in the same way, it may possible that we have a current source, but the value of that current source is controlled by some voltage across some element available in that particular circuit. That's why it is called as voltage controlled current source. In the same way, under this particular domain, again we have two subclasses. It may possible that we have a voltage source and the value of that voltage source is controlled by current. So here we need to write Cc, where Cc indicate current controlled voltage source. In the same way, it may possible that we have a current source indicated by symbol Cs and the value of that current source is controlled by current. So here we need to write Cc. Here Cc indicate current controlled current source. So let me abbreviate this so that you can remember all these type of dependent sources. So basically, as far as electrical domain is concerned, we have four different types of dependent sources. First one is called as voltage controlled voltage source, which is nothing but voltage controlled voltage source. In the same way, second is voltage controlled, but it will be a current source. So here it is voltage controlled current source. Or third is like current controlled voltage source. So Cc stand for current control. current controlled voltage source, and in the same way we may have current controlled current source. So current controlled current source. So these are the four different types of dependent sources which are normally available in any electrical circuit. Now let us try to identify that how to represent them or represent this type of symbols. So first is voltage controlled voltage source. So ultimately it is nothing but a voltage source. Remember one thing, that dependent sources are indicated by symbol diamond shape. This is very important. The moment you have diamond shape symbol for the representation of sources in a circuit, by default those are nothing but your dependent sources. So this diamond structure is by default kept common or kept standardized for dependent sources. So this you have to remember. Now depending upon whether we have voltage source or current source, we may have a fixed polarity representation for symbol or arrow indication for current symbol. So suppose if you are interested to find out how to represent this voltage controlled voltage source, so this we can represent like this. Because it is a dependent, that's why we need to take a diamond. Now, voltage source are always indicated by fixed polarity, like plus and then minus. So the moment we have diamond, and in that diamond we have plus minus, so by default it is going to be a voltage source. It may possible that it is a voltage control voltage source, or it may possible that it is a current control voltage source. But the thing is that if we have a diamond, and in that diamond we indicate fixed polarity, by default this is going to be a voltage source. Now let us try to find out whether it is a voltage control or it is a current control. Now suppose the magnitude of this voltage source, if I define in terms of voltage, for example say 10V, where 10 indicate a constant number and V indicate the voltage across any element available in that particular circuit. For example, if this voltage source is connected in a circuit, and in that circuit we have a resistor, and the voltage across that resistor is say V. So the movement voltage across this resistor is going to vary. Based on that, the magnitude of this voltage source is also going to be vary. For example, initially the voltage is say 1 volt, then the magnitude for this voltage source is 10 into 1, which is nothing but 10 volt. Now suppose if this voltage is say 2 volt, then in that case 10 into 2, which is nothing but 20. So now this voltage source is going to supply 20 volt as an output. Because the value of this voltage source depends upon the voltage across this particular resistor, that's why it is called as voltage controlled voltage source. So this is the symbol for voltage controlled voltage source. In the same way, suppose we are interested to define the symbol for current controlled voltage source. Because it is a voltage source, that too dependent, there has to be a diamond shaped structure with plus minus polarity. So this indicate that it is a voltage source, that too dependent. And because the value of this voltage source is depends on current, so here we need to define this in terms of I. So let's consider that I have indicated that this is 2I, where 2 is a constant term or factor, and I indicate a value of current flowing through some element connected in the same circuit. For example, uh, if this voltage source is connected in a circuit where we have a resistor, and the current flowing through that resistor is indicated by a symbol say I. So this I decides the magnitude for this voltage source. That's why it's called as current controlled voltage source. For example, initially the value of current is say 1 ampere. Then in that case, this voltage source is deliver a voltage of 2 into 1, which is nothing but 2 volt. In the same way, if this I is say 2 ampere, then in that case, this voltage source is now going to deliver a voltage of 2 into 2, which is going to be equal to 4 volt. That means the value of this voltage source is decided by the current flowing through this particular resistor. Hence, it is called as current controlled voltage source. In the same way, same topology we can indicate for representing the symbol for current sources. Because it is a dependent, that's why we need to take diamond shape, and inside that if we indicate arrow, so this define that it is a current source. Now again, whether this current source value is depends on voltage or it depends on current, depending upon that we may have two different types of current sources. It may possible that the value of this current sources depends upon a voltage across any element connected in the same circuit. For example, say 2V. Now this is going to be your voltage controlled current source, where we indicate the voltage across this particular element. So suppose initially the value of V is say 1 volt, then in that case this current source is capable to supply a current of 2 into 1, which is nothing but 2 ampere. In the same way, if the voltage across this element is say 2, then in that case 2 into 2, this current source is capable to supply a current of 4 ampere as an output. So this is for voltage controlled current source. In the same way, we may represent this like current controlled current source. So ultimately it is a dependent, that's why we need to take a diamond shaped structure followed by arrow indication. So this is nothing but a current source. And suppose the value of this current source is dependent on the circuit current. For example, it depends on I. So we need to define this as say 10I. It may be any number. The thing is that this 10 indicate the factor and this I indicate the value of this current source depends on the current flowing through resistor R, which is nothing but I. So initially if you take I as 1, then in that case this current source is capable to supply a current of 10 ampere, because 10 into 1 is nothing but 10 ampere. So 10 ampere. In the same way, if you take the value of current as say 2, then in that case 10 into 2 is nothing but 20. So this current source is capable to supply a current of 20 ampere. That means the value of this current source is decided by the current flowing through this resistor. That's why this is the symbol for current controlled voltage source. So this is very important, and you have to remember this. So finally, we conclude that if we are having a dependent voltage source, it must be a diamond shape with fixed polarity, plus minus, like this. So these are nothing but your voltage source. Here again it is nothing but a voltage source. Now suppose we defined the magnitude of this voltage source like 20V. Now in this case, this V indicate the voltage across certain element available in the same circuit. Now this is called as voltage controlled voltage source. Now suppose if we define the magnitude of this voltage source as 2I, where 2 is the factor and I indicate the value of current flowing through certain element connected in the same circuit. Now because the magnitude of this voltage source is decided by current, that's why it is called as current controlled voltage source. In the same way, if you have a current source that too dependent, so we must take a diamond shaped structure indicated by a symbol. So this is nothing but your current source. In the same way, again here we have a diamond shaped structure followed by arrow. So this is current source. Now suppose the value of this current source is decided by voltage across certain element connected in the same circuit. So this is say 20V. So 20 is the factor and V indicate the voltage across certain element connected in the same circuit. So because the magnitude of this current source is decided by voltage, that's why it is called as voltage controlled current source. In the same way, it may possible that the magnitude of this current source is decided by a current flowing through certain element connected in the same circuit. It may be say 2I, where 2 is the factor and I indicate the value of current flowing through certain element. Then it is nothing but a current controlled current source. So this is very important. It is not at all necessary that it is always going to be a 20 volt or 20V or 2I. It totally depends upon the circuit configuration or not. The thing is that I have just taken an example So this you have to remember. Now based on this, let us try to solve one simple numerical. So whatever the topic which we have covered in today's session, let us try to solve a simple numerical on this. Now let us consider that we have a circuit and our objective is to find the value of voltage or power across that particular circuit. So the circuit is something like this. Here we have a circuit something like this. So this is a circle with fixed polarity. So but obviously this is going to be a practical voltage source, or you can treat this as a ideal voltage source too, and the value is 20 volt. In the same way, or you can say 20 volt. In the same way here, we have another circuit element like this, and the current flowing through this circuit element is indicated by symbol I, and the magnitude of that I is 5 ampere. And here we have the voltage developed across this element, which is 12 volt. And then somewhere over here we have another circuit element, and the voltage across this circuit element is indicated by polarity plus minus 8 volt, and the current flowing through this circuit element is say 6 ampere, which is flowing in downward direction. And somewhere over here we have a diamond shaped structure. The moment we have diamond shaped structure, that means now it is going to be a dependent source. And then in this I have indicated an arrow, that means it is a current source, and the magnitude of this is 0.2 into I. Now see here, 0.2 is nothing but a factor, and I indicate that it is a current controlled current source, because it is a current source. Why it is current source? Because it is a diamond, that to arrow, that's why it is a current source. And the magnitude of this current source depends upon I, where I is the current flowing through this particular element, which is nothing but say element 1. So this is the example for current controlled current source, and the circuit is closed like this. And here we have indicated the power across each element. For example, the power across element 20 volt is P1. In the same way, power across this element is say P2, and here the power across this element is say P3, and here the power across this element is say P4. And our objective is to find the value of these power. What is the value of P1, what is the value of P2, what is the value of P3, and what is the value of P4. This we need to find out. In the last lecture I told you that in order to find the value of power, we need to apply some sign convention, whether it is active or passive. Based on that, we need to take the value of power as positive or negative. For example, if we have an element, and to that particular element, if a current is entering through positive terminal, then this element is treated as a passive element. For example, in case of resistor, we know that current always flows from higher potential to lower potential. So this is plus and this is minus. So this is nothing but resistor. So in case of resistor, the current is always going to enter through positive terminal. And we know that resistor is nothing but passive. That's why if you have an element, and to that particular element, if current is entering through a positive terminal, that we can treat as a passive element. And passive elements are always going to consume energy, or they are going to store energy, they will not supply. And the moment they are not going to supply power, that's why for passive element we are going to treat power as negative. This is very important. This we already discussed in the last lecture. In the same way, if suppose we have an element and suppose to that particular element current is leaving through positive terminal, then that particular element we are going to treat as active. Now why it is so? Now see here, suppose if you have a voltage source, say plus minus, and we know that voltage source is always going to supply energy, or you can supply power. So as far as voltage source is current consider, the value of current is always going to leave through its positive terminal. So here we have I. So current is leaving through positive terminal, that's why this particular element we are going to treat as an active element. And active elements are nothing but a kind of element which are capable to supply energy or supply power, and hence in this case we are going to treat power as positive. So this you have to remember. For example, if you have an element, and to that element if the current is entering through positive terminal, then that element is going to be passive, and for passive, power is negative. And suppose if you have an element through which current is leaving from the positive terminal, that means it is nothing but active. Active, power is going to be positive. So this sign conventions you have to remember, and I'm going to apply the same sign conventions in order to solve this numerical. This is very, very important. So ultimately our objective is to calculate the value of this power. So how to solve this? Apply the logic and try to find out the value for this. It's very simple. See here. Now in this case, our objective is to find the value of P1, P2, P3 and P4. So first, let us try to find out the value of P1. So what is P1? P1 is nothing but the power across this particular element. So this element is nothing but a voltage source, and in the circuit it is given that this voltage source is capable to supply a current of magnitude 5 ampere. So here I am going to indicate that current, it is nothing but 5 ampere. Now see here, through this positive polarity current is leaving out from this circuit, so this element is going to be an active element. And the mathematical formula to calculate power, it is simply the product of V into I. So what is V? The voltage supplied by this voltage source is 20 volt, so it is going to be 20 multiplied by I. What is I? It is nothing but 5. So 20 multiplied by 5, answer is 100 watt. And what will be the sign for this? Because it is a active element, see, the current is leaving through positive polarity, and for active we are going to take power as positive. That's why this is going to be plus 100 watt. I hope this is clear to everyone. Now let us try to calculate what will be the value of power across element 2, which is nothing but P2. Now see here, across element P2, here we have a voltage indicated by symbol plus minus, and the magnitude is 12 volt. And through this particular element current is entering through positive. See, this is a positive polarity and the current is entering through positive polarity. So this is a kind of your passive element. So first of all, let us try to calculate what will be the magnitude for this power. So power P2 is going to be equal to V into I. So what is V? This is 12 into what is I? It is nothing but 5. So this is going to be 60 watt. And what will be the nature for power? Because it is a passive element. See, here we have that element. This is plus minus of magnitude 12 volt, and the current is entering through positive terminal. When a current is entering the positive terminal, this is treated as passive, and in passive power is negative. So this is minus 60 watt. Now let us try to find the value of power across element 3 or P3. So see, across element 3 we have a voltage of polarity plus minus 8 volt, and the current is entering through positive terminal. Now because current is entering through positive terminal, it is going to be a passive, and in passive power is nothing but negative. So here I am going to write minus, and then let us try to calculate what will be the magnitude for this power. So it is simply V into I, where V is 8, and what is the value of I? It is nothing but 6. So it is 48 watt, that too negative. Now let us try to calculate the value of power across element 4, which is nothing but P4. Now this is a kind of your dependent source. So first of all, we have to calculate what is the value of this current controlled current source. Now see here, the magnitude of this current controlled current source is defined like 0.2 into I. That means it is a kind of your current source, and the magnitude of this current source is dependent on the value of current I. Now what is I? I is nothing but the value of current flowing through this particular element, which is nothing but P2, and in this case the value of I is nothing but 5 ampere. So first of all we have to calculate the value of this current source. So value of this current source is 0.2 into I, and I is 5 ampere. So I can write this as 5 into 2, which is 10. So this is going to be equal to 1 because we have 0.2. So 1 ampere is the value for this particular current source. Now let us try to find out what will be the voltage which is available across this particular element. Now see, this element P3 and this element P4 are connected in parallel, and we know that in parallel combination voltage will remain same, and in the circuit is given that voltage across element P3 is 8 volt. So the same 8 volt is going to appear across this controlled current source. So here we have 8 volt as an output. Now see here, because this particular source is going to supply a current in this particular direction, and the magnitude of that current is 1 ampere, so I can treat this particular element as an active. Why? Because current is leaving from positive terminal. So this is going to be plus, and let us try to find out what will be the magnitude for this power. So it is simply the product of V into I. So here V is 8 multiplied by I. So I we have already calculated, which is nothing but 1. So this is going to be equal to plus 8 watt. So in this way we are in a position to calculate the value of power across each element. The beauty is, depending upon whether they are active or whether they are passive, we have to indicate a sign convention. So what sign convention we have follow? So the sign convention we follow in this circuit is nothing but, for passive element power we have taken as negative, and for active element power we have taken as positive. Why we have taken positive? Because active elements are going to supply power, that's why positive. Passive elements are going to consume or store power or energy, that's why negative. So from this it is very clear that because P1 and P4 are positive, see, positive 8 watt, positive 100 watt, that's why P1 and P4 are active element, whereas P3 and P2, or you can say P2 and P3, both are negative. See, minus 60 watt and here minus 40 watt. That means they are not active element, they are passive element as far as this particular circuit is concerned. So in this way, we can solve numerical on power calculations as well as how to find out the value of dependent source based on circuit behavior. In the next class, we will continue with our syllabus. Thank you.